Hi, I'm Professor Goins. Welcome to the Math Professor's YouTube channel. We post videos on topics throughout college mathematics, beginning from algebra, statistics, to calculus, and more advanced topics as well. If that's something that you're looking for, please consider subscribing and checking out some of our other videos. As you can see, I'm using a slightly different presentation technique here. I'm trying out a light board as opposed to the traditional whiteboard that I usually use. I'd be curious to know what you guys think. Go ahead and post in the comments below if you think the whiteboard that I usually use or this light board makes for a better presentation. Be curious to see what you guys think. Let's get into the current video. What I want to do is take a look at solving first-order linear differential equations using what's called a Laplace transform. Now, in this video, I'm going to go ahead and assume that you've seen Laplace transforms before, that this is not your first exposure to a Laplace transform, because I'm going to then use those to solve some initial value problems. Now, the first thing I want to take a look at is when I take the Laplace transform of a derivative. So if I take the Laplace transform of a derivative, what do I get? Okay. Well, the definition of the Laplace transform is the improper integral from 0 to infinity of e to the negative st, and then the function that I'm taking the transform of, dt. Okay, so this is the definition of the Laplace transform, and it just applied to the first derivative. To evaluate this integral, I'm going to use a u substitution. So let's go ahead and set up our u substitution table. So I've got my u, my du, my dv, and my v. And I'm going to set u is going to be e to the minus st, and then differentiate that with respect to t to get my differential of u is going to give me negative s e to the negative st dt. And then for my dv, part of the integration by parts, I'm going to use f prime of t dt, right? It's going to be the rest of the integrand along with the differential. And then I go ahead and take the antiderivative, which gives me f of t. Okay. Now, integration by parts formula says that the integral is going to be equal to uv minus the integral of v du. So therefore, this is equal to e to the negative st f of t, and that's going to be evaluated from 0 to infinity, minus the integral from 0 to infinity of negative s e to the negative st f of t dt. Okay. Now, certainly I can take those two negatives here and turn that into a positive, so let's just go ahead and get rid of that. Now, as far as evaluating this part of the integrand, or this part of the antiderivative from 0 to infinity, remember that in order for a function to have a Laplace transform, it has to be of exponential order, meaning it's eventually bounded by an exponential, and therefore when I take the limit at infinity of e to the negative st f of t, I'm going to get 0. Right? That's in order for the function to have a Laplace transform, it has to be of exponential order. And then minus the part of the antiderivative evaluated at the lower limit of integration being 0. Plug in 0 for t, I get e to the 0, which of course is 1, and then I would get f of 0, so the function evaluated at 0. Then if I look at this integral, this is the definition of the Laplace transform applied to the function f of t, and therefore this is simply the Laplace transform of the original function. And let me just go ahead and clean that up. I get the Laplace transform of the function minus the function evaluated at 0. One thing that I forgot to add here is notice that the definition of Laplace transform is the integrand is the exponential times the function. We have an extra factor of s here, so that's actually going to be s f of s, and then this is s f of s. And taking a look at the very beginning to where we ended, if if I take the Laplace transform of a derivative, what I get is the quantity s times the transform of the function minus the original function evaluated at 0. And this is what I'm going to use to convert differential equations to algebraic equations, because I can go from a derivative to just functions. And that really kind of hits the highlight of what the Laplace transform even does. So over here, let's take a look at just sort of a schematic diagram of what the Laplace transform accomplishes. What I do is, of course, we're taking differential equations, so our main focus here is solving differential equations. And certainly what we want to do, of course, is we want to solve those. So here's one path, as I could just solve the differential equation if we have a method for that. And this is the differential equation solution, right? If I can use, say, characteristic equation or an integrating factor, whatever the case may be, we might have a solution, we might have a technique for solving that differential equation. However, there is another way to do that, which is highlighted here. If I take the Laplace transform of a derivative, I get something algebraic. So if I apply the Laplace transform to a differential equation, what I end up with is an algebraic equation. Certainly algebraic equations are simpler to solve. So therefore I'm going to solve this, and we end up with a solution to the algebraic equation. So I'll call this the algebraic solution. Right, but remember that the goal is to get the solution to the differential equation. So how do I go from the algebraic solution to the differential equation solution? Well, the answer is pretty straightforward. I use what's called an inverse Laplace transform. Now, in this current course, in your differential equations course, you're going to use tables to find inverse Laplace transforms. You are not going to compute those directly. Computing those directly will require complex analysis, which is beyond the scope of this current course. So we will then use tables, a handful of which you'll probably have memorized because you'll use them so frequently. Any more, esoteric ones or ones that don't come up as often, you'll probably be provided with the table, say, on your exam. Okay, but I can't speak for, obviously every class out there. So let's go ahead and let's take a look at how do I solve a differential equation using a Laplace transform. In particular, first order linear ordinary differential equations. So let's take a look at dy dt minus, say, 5y is equal to 0, and let's also say this initial value y of 0 is equal to 3. So once again, I have what's called an initial value problem, meaning it's a combination of a differential equation along with an initial value of the original function that I'm trying to discover. Okay, so let's go ahead and take a look at the solution for this. And once again, we're going to follow the schematic diagram that I have up here. We're going to take the differential equation, we're going to apply the Laplace transform, we're going to construct an algebraic equation, we're going to then solve the algebraic equation. Once I have my algebraic equation, I'm going to apply an inverse Laplace transform to it, which is going to give me a solution to the original differential equation. Now, this one it's a pretty simple differential equation. We could use alternative techniques to solve this. Using a Laplace transform is, quite frankly, overkill in this case, but I'm wanting to illustrate the method, which is the more important part of this. So let's go ahead and apply the Laplace transform. So I take the Laplace transform of both sides. Okay, and Remember that the Laplace transform is a linear operator. Therefore, the left-hand side is the Laplace transform of the derivative, again, which is what we had discussed over here, minus 5 times the Laplace transform of the original function, or the unknown function. And then on the other side, the Laplace transform of 0 is simply 0. Okay. All right, now let's use the result that we had just discussed at the very beginning of what the Laplace transform of a derivative is. Remember, that's the variable s times the transform of the unknown function minus the initial value of the unknown function, and then minus 5 ly is simply the Laplace transform of the unknown function, so this would be minus 5. Capital F, remember, is the Laplace transform of the lowercase function f, and this is equal to 0. All right, I'm going to use my initial value that we gave over here, which is y of 0 equals 3, and I get s f of s minus 3 minus 5 f of s is equal to 0. All right, let's see where we are in our diagram here. What we did is we just applied a Laplace transform to a differential equation, and we came up with the algebraic equation. My next step in this diagram is to then solve the algebraic equation to come up with an algebraic solution. Well, I can combine the capital F of s and factor out s minus 5, and then I can add 3 to the other side, and that would give me f of s is equal to 3 over s minus 5. Okay, so this is the algebraic solution. Remember, lowercase f, or y equals f of t, is the unknown function. Capital F is the transform of the unknown function, meaning this right here is the transform of the unknown function. And now what I have to do to get back to my differential equation solution is use an inverse Laplace transform. One thing, again, this is what you would find, say, in a table of values. So let's just call this a note here. So note, the inverse Laplace transform of an expression 1 over s minus a is equal to e to the a t. So again, that would be a result that you would get from a table in your textbook. And also, just like the Laplace transform, the inverse transform is linear. So if I've got a factor of, say, 3 in the numerator, I can just pull that out front and just multiply it as my coefficient for the function. So therefore, if I were to take the inverse Laplace transform of both sides, so the inverse Laplace transform of f of s is equal to the inverse Laplace transform of 3 over s minus 5. On the left-hand side, the inverse transform of a transform is the original function, so that's y of t. On the right-hand side, again, due to linearity of the inverse transform, I can just pull that 3 out. And then I've got the transform of 1 over s minus 5. 5 matches up with a, and notice it's minus a minus 5, so it's in the same format, and therefore this would be e to the 5t. And this would be the solution to the differential equation. In other words, that would be the answer that we would have in this spot. So if I was able to solve this a different way, for example, you could just use an integrating factor, or there's different ways you could solve that. We would come up with the same solution, so we could actually solve it directly as opposed to going through this schematic diagram. But be that as it may, that is the solution to the initial value problem. Okay, so why don't we take a look at one more example. Let me leave this schematic diagram up here. Let me clean up the rest of the board. So let's try let's try this one. The first example I did was a homogeneous. Now let's do a non-homogeneous equation, but we'll use the same method. Okay, so solution. Apply the Laplace transform to both sides. So Laplace transform of the left side and again, we could write out the next step where I separate this using linearity, but we know that it's linear, so I'm just going to go ahead and write the result. The Laplace transform of the derivative is f of s minus y of 0 minus 2 f of s. And the other side of the equal sign, the Laplace transform of the exponential e to the t is 1 over s minus 1. Now, I suppose in the very beginning, I only give you a differential equation. I did not provide the initial value. We could leave this as just a generic constant and just have a generic constant in my final solution, but let's go ahead and give an initial value, and let's say y of 0. Just for simplicity, let's say y of 0 is 0. Okay, so then let's go ahead and again, we just applied the Laplace transform to come up with my algebraic equation, and now let's come up with the algebraic solution. I'll do it the same way, right? I'm going to factor out, actually, I'll try to use the same color here. Let's go ahead and factor, oh, I didn't. Sorry, on my end here, I'm still getting used to the light board. The color is kind of, it's kind of hard to tell the difference sometimes. So I think we're good here. So let's go ahead and f of s and s minus 2. So I factored out s and then negative 2, and then y of 0 we said was 0, and this is equal to 1 over s minus 1. Okay. Therefore, the transform of the function, giving me the algebraic solution to the algebraic equation, is 1 over s minus 1 times s minus 2. Okay. So that is the algebraic solution. Now we have to use an inverse transform to get back to the solution to the original differential equation. In order to do that, well, you can see that in the denominator I've got factors of, say, s minus a, which is what we had corresponding to the transform of the exponential function and then the corresponding inverse transformation. Well, we can separate this, right, using a partial fraction decomposition. So let's do that over here. Let's see if I have enough space for it. So the partial fraction decomposition, 1 over s minus 1, s minus 2 is going to be an unknown constant a over s minus 1 plus b over s minus 2. Okay, and then let's go ahead and clear the denominator. So I'm going to get 1 is equal to a times s minus 2 plus b times s minus 1. And then I'm going to choose values for s to correspond to making different factors 0, which will allow me to solve for the different constants. If if I say s is equal to 1, then I get 1 is equal to a times, well, 1 minus 2 is negative 1, and 1 minus 1 is 0. Therefore, the value of a is negative 1. And then if I choose the other convenient value of 2, I get 1 is equal to, well, of course, the a term now is 0. The b term is going to be b times, well, 2 minus 1 is 1, and therefore the value of b is 1. That means if I take the partial fraction decomposition, I can rewrite this as, so remember that a was the coefficient on top of s minus 1, which was negative 1. That gives me negative 1 over s minus 1 plus the coefficient on top of the s minus 2 was 1, so that's 1 over s minus 2. Okay, and again, this is the transform of the unknown function. Well, finally, we can apply the inverse transform. And I'm going to do that over here. So finally, the inverse transform, oh look, I think I used the wrong color there. Oh well. I'll apply the inverse transform. Okay. Of course, the left-hand side is the inverse transform of a transform, therefore the original function. And on the other side, it looks like I'm going to have a linear combination of some exponentials. Negative 1 over s minus 1 is going to be negative e to the t, and then plus 1 over s minus 2, the transform of that, or more precisely the inverse transform, which is still a transform, but this is going to be plus e to the 2t, and this would be the particular solution or the exact solution of the initial value problem. Okay, in subsequent videos we'll take a look at higher order differential equations, and we will also take a look at maybe some more complicated equations, but I just wanted to give you an idea of how to solve differential equations using a Laplace transform. What is the idea all about? And again, it's all encoded in this schematic diagram that I have right here. Thank you for watching, and consider subscribing.